All right, welcome back, everybody. Today we're going to be doing section 14.8, so we're rounding out chapter 14. This is the last section of chapter 14, and this one is all about Lagrange multipliers and the Lagrangian. So let's get started. I'll pull up the slides right here. Okay. Good news is this one is a little bit technical, but shouldn't be very long. So the last one was kind of a long lecture. This one shouldn't be as long, but it might be a little more technical, all right? So here's the overview. We're going to just develop the theory of what we're doing with Lagrange multipliers. We will provide the definition of the Lagrangian itself, which is basically the thing that we're going to optimize, the function that we're going to optimize. Discuss the method of Lagrange multipliers. We'll do an example with problems with one constraint, talk about problems with two constraints, and then generalize the technique to higher dimensions and problems with multiple constraints. All right, so yeah, let's get started. So you might remember in the last section, 14.7, there was that question where we maximized the volume function of a box, and we maximized it subject to the constraint that the surface area had to be 12, and that constraint was given in the form of this equation right here, right? So this mathematician, Joseph Louis Lagrange, developed a simpler method for optimizing such functions given a constraint. So in particular, what he did was he developed a method to maximize a function f of x comma y comma z subject to a constraint of the form g of x comma y comma z equals k for some real number k. So what we're going to do, just to get some intuition and to talk about how this works, we're going to develop the theory by exploring two variable functions, but it extends to any number of variables and any number of constraints, even infinitely many variables. So you can actually generalize this process to functions of infinite variables. We won't go there though. So here's the setup. Here's the idea. So try to conceptualize this and think about this as we go along. So suppose we have a function f of x comma y, and we've got another function g of x comma y. And what we want to do is we want to find the extrema of f given a constraint defined by this equation here, g equals k, for some real number k. So maybe as like a non-geometric, non-purely abstract example, you could think of something related to business. So what if we had a two-variable function for revenue and we had another two-variable function for the budget? Well, the budget constrains our operation in some way. So that's going to affect our revenue. And what we want to do is we want to maximize our revenue given the budgetary constraint. So this gives you a little bit of motivation for like why we care about this and what you could use this for. Remember, this is mathematics, so it can be used for a lot of things. Do I know what you're going to use it for? No idea. You might use it for this. You might use it for some engineering application, for some physics application. I don't know. The point is the tools are here. We have the tools, we have the technology, and we can do what you're interested in. That's the cool part about math. So let's look geometrically at what we're talking about. So geometrically, we are trying to look at two surfaces that intersect. So here's the first surface. That's a surface in R3. And this is also going to give us a surface in R3. And these surfaces might intersect somewhere, right? Now, remember that this equation here, g of x comma y equals k, that represents a level curve of our function g, right? Setting that output equal to k, and we can look at a level curve. In this case, this is what it looks like in the image, the figure here. So what we're really doing when we are looking for the extreme values of f subject to this constraint is we are looking for extreme values of f when the point x comma y is required to lie on this level curve for g. So this is a moment where I want to pause. I just want you to kind of stare at this and think about it for a minute before I go forward. Okay, so if you look at the figure here on the right, you'll see that there is an intersection, and the intersection occurs when the level curve here for G touches a level curve of F. In this case, it's right here, right? So what that means is that at this very, very special point here, these two curves share a tangent line at that point. So the tangent line is tangent to both of the curves at that very point, that point of intersection, okay? We'll say the point is x naught, y naught, just for ease. Now, because the tangent line is the same, that means that the normal line at that point has to be the same for both curves too. So that means that the gradient vectors are parallel. So remember that the gradient vector like does this. It gives you the it gives you the direction of steepest ascent, right? And the gradient vector is always orthogonal to these level curves, right? So because we have this intersection point, the gradient vector of f and g have to be parallel. They have to be parallel. So because they're parallel, that means there exists some scalar, lambda, such that the gradient of f is equal to lambda times the gradient of g. That's what it means for two vectors to be parallel, right? So another way we can write it is like so. And this is the preferred way of writing it because as you're going to see, this converts the problem into one of a root finding problem where we're just trying to find the zeros of a function. So subtract that from this side and you get this. So this characterizes exactly the scenario that we are looking to solve, I'll just say. Here we go. And this gives us the definition of a Lagrange multiplier and the Lagrangian. So that number lambda right here, that scalar, that is what is called a Lagrange multiplier. And typically what you do is you formulate this problem of this optimization problems in terms of a function that's called the Lagrangian. So the Lagrangian function is this function right here, this difference function, the difference between gradient f and lambda gradient g. And here I'm actually just writing it for, I'm writing it for an arbitrary number of variables. So x can be, this is like a vector x, right? So this actually holds for any number of variables, right? And what we're doing is we're looking at this difference function and we want to find the zeros of this difference function. When we find the zeros of this difference function, we've now found the points x, y, and lambda and beyond where this is actually going to zero out, all right? Now, one very important detail I want to make here or point out here is the way that I am introducing this process is different than the way the book introduces it. What I'm going for is a process and a technique that is more generalizable and that is more systematic, you could say, because what you're going to notice very quickly is that this is not the kind of process that you really want to do by hand. You could do it by hand, but again, it's much easier to recharacterize the problem in terms of a function and finding the zeros of a function. That's, oh yeah, I'm sorry, we're not finding the zeros of this, we're finding the zeros of the gradient of L. So that's one thing I want to say is that the way that I introduce this differs from what you will read in the book. The other thing I want to mention here is that in this formulation of the problem, g of x already includes the given constraint of k. So if you look back at these pictures, right? So here it says g of xy equals k. What I'm saying is that in this formula here, g of x is really some function minus k. Sorry, some function minus k. So our constraint is going to be given in this form, where g of x equals 0. So the k value, that constant value, is already wrapped up inside this function, whereas here it is not wrapped up inside that function. Okay, I'll show you what I mean when we do an example. But that's what this says. The constant k is included in our formula for g of x. Okay, so this function here is what we call the Lagrangian. You use a little fancy L. It's a function of any number of variables as well as the variable lambda. So, you know, if x is 2 variables, this would be a function of 3 variables and so on. If x ended up having 4 variables, then this would be a function of 5 variables and so on and so on. And that's the idea. Okay. So here is the method of Lagrange multipliers. Here is like literally what we're doing with this method. To find the maximum and minimum values of some function f subject to the constraint g of x equals 0, assuming the extreme values exist, and assuming that the gradient of g is not 0 on the surface, on the surface given by this is what we're trying to do. We want to find all the values of x and lambda such that the gradient of the Lagrangian is 0. So this is basically why it's nice to formulate the problem in terms of the Lagrangian. This is what we're trying to solve. We're trying to solve gradient of L equals 0. That is what you want to solve. Find the zeros of this function. That's it, okay? Once we have found all the zeros of this, of this gradient of L, evaluate your function f at all of those values, and the largest of the output values is the maximum, the absolute maximum, and the smallest is the absolute minimum, given that constraint, the constraint here, okay? Just to give you a quick and easy example, this one, maybe I won't say easy example, yeah. Let me do this one. Let's do this one together. Instead of you trying to do this all on your own, let's do this one together so you can see how it works. So let's find the extreme values of this function on the circle, x squared plus y squared equals 1. That's the goal. So we have this surface in space, but we want to restrict our attention to this circle and see basically where are the maxes and mins if we restrict ourselves here, okay? So what does this really boil down to? This amounts to finding the extreme values of f on the curve of intersection of f and the cylinder, x squared plus y squared equals 1. So before, I don't want to show you an image yet, but I have a figure in a couple of slides. What I just want you to try to imagine is there's some surface, and it's getting intersected by a cylinder, and the intersection is some curve on that surface, and we want to know what's the maximum value of f on that curve. That's the idea, okay? So here's what we do. We encapsulate this constraint by writing g of xy equals x squared plus y squared minus 1. So this is what I meant by the k value is wrapped up in our constraint function already. So this is what I meant when I said this, okay? So this is one way that this explanation differs from what you see in the book. And really it just boils down to subtracting k. And that's why you're going to write your g function. So here we go. G of x comma y is this, x squared plus y squared minus 1, right? And then when this is 0, when g of xy is equal to 0, that gives you this. That's it. Now, let's construct the Lagrangian. So the Lagrangian is going to be a function of x, y, and lambda, because lambda is another variable that's getting tossed in here. That's the Lagrange multiplier. This is what it is. So it's f minus lambda g. This is what it looks like when you substitute in the values for the function. And now we're going to compute the gradient. So you compute the gradient of the Lagrangian just like we did in the previous sections, right? Partial with respect to x, partial with respect to y, and then partial with respect to lambda. So here we go. Differentiate this with respect to x, and you get this. Differentiate this with respect to y, and you get this. Then differentiate this with respect to lambda, and you get this. All right? So that's the gradient of the Lagrangian. Now what we want to do is this. We're going to set the gradient of L equal to 0, and in doing so, it's going to generate a system of equations that we then have to solve. So setting the gradient of the Lagrangian equal to 0, you get a system of 3 equations in 3 variables, x, y, and lambda. Here is the system right here. L sub x is equal to 0, L sub y is equal to 0, L sub lambda is equal to 0. And then moving things around, you get this. So now you got to realize at this point, all we are doing is solving a system of equations. So whatever technique you use, as long as it's a valid technique, it works. But remember, computers are, problems like these are just ripe for computers to solve, right? Because you're going to end up with a system of equations, and computers are just really, really good at solving those. So the theoretical construction is the important one. Understanding why we are doing this, what the Lagrangian is, what we are finding when we set it equal to 0, that gives you the system itself. Then you can use whatever techniques you want to solve the system. You can use elimination, you can use substitution, you can use a combination of them. You can use Gaussian elimination, you can write a matrix in reduced row echelon form. You can do all sorts of stuff, right? But the point is, setting this gradient equal to 0 produces a system of equations that you then have to solve. So here we go. From the very, very first equation here, we get that either lambda is equal to 1 or x is equal to 0. So that's what this tells us. Maybe I'll even say like this implies lambda is equal to 1 or x is equal to 0. All right, now picking x is equal to 0, if x is equal to 0, if I take that and plug it into this equation, then we get that y must be plus or minus 1. So now we have possible extreme values at these 2 points. There we go. So those are possible extreme values, 0, -1, and 0, 1. Okay. If lambda is equal to 1, that was the other condition, right? If lambda is equal to 1, then the second equation gives that y has to be equal to 0. So let me, if I just do this, if lambda is equal to 1, then that disappears. Whew. Oh, I feel like I have to sneeze. Then lambda disappears, and the only way that 4 times something could equal 2 times something is if that something is equal to 0. So if y is equal to 0, taking that and subbing it into the last equation gives us that x is equal to plus or minus 1. So now we have 2 new potential extreme, or points where extreme values could occur, right? This one and this one. So now we've got 4 possibilities where these extreme values could occur. Here, 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 and here. Okay, now what we do is we evaluate the function f, the original function f, at these points and see what we get. We get 2, 2, 1, 1. There we go. Now let's bring in a little bit of geometry. We found all of the possible maxes and mins on our surface, given the constraint that we have to lie on this curve. So now we can see that the maximum value is 1, and it occurs in 2 places. I'm sorry, not maximum. The minimum value is 1, and it occurs in 2 places. And the maximum value is 2, and it occurs in 2 places. So there's the minimum. There's another one on the other side you can't see. Here. Yeah, here's a minimum. There's another one that's like over here. Here's a maximum, and then there's another one that's over here. Those are the values we just found using this technique, right? So not too bad, right? Not too bad. Oh yeah, I threw this in, just a quick review problem. This is something you should try real quick, just as a little bit of a refresher. Now that you've got this picture and you have this, these images here, try to do this for just a minute. See if you can find a vector function for the curve C up here. All right, try to work that out on your own. Shouldn't take too long, but it's just a good quick review. All right. Okay, next, now we need to talk about problems with 2 constraints. So this is where things are going to start to generalize, right? There are lots of situations where we want to optimize something where we have multiple constraints, right? Where it's like, oh, this has to be true, and this has to be true, and this has to be true. Let's just keep it at 2 for now. So let's suppose that we have 2 constraints that we want to adhere to. We're going to work with a function of 3 variables just to make sense, a little more geometric sense of what's going on. But let's say our function f is now a function of 3 variables. And what we want to do is we want to find the maximum and the minimum values of f given 2 constraints, this one and this one. So g is equal to 0 and h is equal to 0. Remember now what I've got is, oh, see, this is a typo here. This should say 0. This should say 0. Oh, no, that's not a typo. I did that on purpose. So remember what I was saying before, which is we're encapsulating the k and the c values within our function itself. So basically subtract so that you can just write your function as g equals blah, blah, blah minus k, and h equals blah, blah, blah minus c, just to make things easy. All right. Now what we have is we actually have 2 level surfaces. So because we're with a function of 3 variables, we have level surfaces, not level curves. Now there's 2 level surfaces that are intersecting, and we want to find the extreme values of f when our point lies on the curve of the intersection of these 2 surfaces. This thing right here, the curve. Now from before, we know that the gradient of f is orthogonal to this curve at P. That was from oh geez, I forget which section it was, one of the previous sections. So we know that the gradient is orthogonal to that surface, orthogonal to that curve at P. And we also know that the gradient of G is orthogonal to this surface. And we know that the gradient of H is orthogonal to this surface, right? So they're both orthogonal. Now, what this means is that both gradient of G and gradient of H are orthogonal to the curve C, okay? Now, what does this mean? This means that our gradient of F has to lie in the plane determined by gradient G, gradient H. And so consequently, there are numbers lambda and mu such that we can write the gradient in this form. So this is one of those times where, again, I want you to pause and just kind of read this over and actually say something out loud. I haven't done this yet. Say something out loud just to help your brain with that feedback. Right. Okay. Now let me continue here and let me try to give you a little more intuition for what's going on right here. Let's see, how do I say this? Uh, okay. Because both of these things are orthogonal to the curve C, you can see in this picture right here. And we also know that the gradient of F is orthogonal to C as well. Well, because these two things are orthogonal, what we can do is we can write the gradient of F as a linear combination of these other two gradients. Think about vector sums, right? What I'm saying is that if you want to write this vector, you can write it as a scaling of this vector plus a scaling of this vector. And if you think about like geometric vector arithmetic, the sum of those two scaled vectors will be equal to F. That's really what this is saying right here. So maybe if you like stare at this for a minute, and what I'm saying is this vector is equal to lambda times this vector plus mu times this vector. And that's because these two vectors are orthogonal. So in some sense, they're forming a basis. It's not, they're not normal vector, how do I say this? They're not unit vectors, but because they are both orthogonal, they can form a basis. And so what we can do is we can scale each one, add the results, and describe F in that, I'm sorry, gradient of F in that way. That's really what this is saying. So long story short, gradient of F is a linear combination of the gradients of G and H. Lambda is this Lagrange multiplier, mu is this Lagrange multiplier, and there we go. Now, what does our Lagrangian look like? So our Lagrangian is now a function of 5 variables because F was a function of 3 variables. Then we have the Lagrange multiplier lambda, and then we have the Lagrange multiplier mu. So our Lagrangian looks like F minus lambda G minus mu H. And just like before, if we compute the gradient of the Lagrangian and set it equal to 0, we're going to get a system of 5 equations in 5 unknowns, just like so. There we go. So compute all those partials, set them equal to 0. Now you've got a system of 5 equations and 5 unknowns. You can solve the system of equations using whatever technique you want to use for solving systems of equations. That's it. Okay. All right. Now here we go. Here's the moment of truth. Here's one that I want you to try on your own, okay? And then we're going to do it together. So here is the question. Find the maximum value of this function on the curve of intersection of the plane here and the cylinder here. All right? So first just ponder it for a minute. Look at it, mull it over in your brain. Okay, now say something out loud to yourself to give your brain that feedback and maybe get you started. Right, and now try to work it out on your own, and we're going to do it together. Just remember, at some point, you should get to a system of equations, and that's really where the tedium begins, I would say. All right? Okay, now let's do it together. Um, All right, so we have a couple of constraints here. So we have our function, we have our two constraints. We should form our Lagrangian. Yeah, we should form our Lagrangian. So first thing is we're gonna make this constraint be g. And remember, like I was saying before, we're gonna incorporate the constant term into our function g. So we're gonna let g equal x minus y plus z minus 1. And we're gonna let h be x squared plus y squared minus 1. So those are our two constraint equations. Now we can formulate the Lagrangian. It's a function of 5 variables, x, y, z, lambda, mu. Here is f minus lambda g minus mu h. That's the Lagrangian. Now we're going to compute the Lagrangian. So compute all the partial derivatives with respect to x, y, z, lambda, and mu. And this is what you get just for the partials. So I haven't set anything equal to 0 yet. These are the partials. Partial with respect to x of this, partial with respect to y of this, partial with respect to z of this, partial with respect to lambda of this, partial with respect to mu of this. Okay. All right. Now we're going to set our gradient equal to 0. Oops, sorry, this should be bolded right here. This should be a bold 0. So now we're going to set the gradient of our Lagrangian equal to 0, and that gives us the system of equations. So here's from the first one, the second one, the third one, and then these are our two constraints, right? Now at this point, you are in system of equations land. Solve it however you want to solve it. Substitution, elimination, use a computer, anything you want to use. So how did I do it? Okay, we're already given lambda, so this is a nice result. Lambda has already been fixed, or lambda has already been completely determined. It's 3. So since lambda is 3, what we can do is we can plug it into these first two equations and then solve for x and y. I'm not going to go through the algebra here, but you're welcome to do it on your own. Hopefully it looks a little similar to something you did, but it could be totally different. There's lots of ways to solve systems. But if you plug in 3 here and here, and then you solve this for x, and you solve this for y, you should get these two results. All right, so now we've written x and y in terms of mu. And so what we can do is we can take those results and plug them into this equation right here. Doing that gives us this. And then now we can solve for mu. That's what we're going to do next. So here's the solution for that. You get this, mu squared is equal to 29 over 4. Take the square root of both sides and you get a plus or a minus. So that means mu could be plus or minus square root of 29 over 2. Now that we know what mu is, we can go back to these equations and figure out what x and y could be. So it's going to get a little bit messy here, but x could be, or x is equal to this, and y is equal to this. Try not to get weirded out by this symbol. This symbol is just minus plus instead of plus minus. It is virtually equivalent to plus minus. I just like to use it in the cases where there's an additional negative, so it kind of changes the sign, right? So like x was negative 1 over mu, but mu is plus or minus, so negative plus or minus is minus plus. But it really doesn't matter. It could be either or, right? So here's possibilities for x. Here are the possibilities for y. We already know lambda, and we just found two possibilities for mu. All right, here's where the mess comes in. So by equation 2, I lost track of what equation 2 was. This one. So by this equation right here, we can plug in our values, our possible values for x and y to find what z is going to be. Here we go. So z is equal to this, and I'm just going to substitute what we already had for x and y. X, y, x, y. And then when you simplify this, you're going to get that z is equal to 1 plus or minus 7 over root 29. Right. Now we can evaluate the function at these points. So you can plug these in individually. I'm just saving some space by plugging them all in at once. You're going to get this. So here's x, y, z. And then these are the values we get. So at those points, those are the two possible minimum and maximum values. So what is the maximum value? Behold, it is 3 plus square root of 29, the larger of the two, right? And that is it. That is it. Okay, next, let's extend it to higher dimensions and multiple constraints. Again, none of this is restricted to 2 or 3 or any number of dimensions. It's just however many you want, however many constraints you have. So as you can see, the process is very tedious, but to do by hand, but it's systematic. It's systematic so it can be automated. And this is one of the reasons we like computers. Humans come up with the theory, and then we have computers to go through the really, really dirty, tedious work of it, right? In essence, like I mentioned this already, in essence, all this is boiling down to is a root finding problem. And root finding problems are everywhere in math and science. Pretty much you do everything you can to convert your problem to one where you're finding roots, finding zeros. And then once you've got that, once you've formulated your problem in that context, there's like thousands and thousands of algorithms you can use to find roots. So we're just trying to find the roots of the gradient of the Lagrangian. That's all we're trying to do. Now, in practice, there could be any number of variables and any number of constraints, so now we're going to generalize it. Here we go. Suppose that we have a function f of x of n variables, and we're going to let x be this vector, so x1 all the way to xn. And suppose we have m constraints given by the functions g sub k of x, all right? Or maybe I should say equals 0. I'll fix that by the equations g sub k of x equals 0. So you have one constraint equation for each k going from 1 to m. All right, then that means there are m corresponding Lagrange multipliers. We'll call them lambda sub k, one with respect to each gradient of each g. All right, okay. To simplify the notation, because the result here is really, really quite beautiful. Yeah, just really, oh, wait. Yes, that's right. Yeah, really quite beautiful. Let bold lambda be the vector that contains all of the Lagrange multipliers, right? And let bold g of bold x be the vector that basically contains all of our constraint functions, you could say, right? So g1 of x, g2 of x, gm of x. Then finding the maximum and minimum values of f subject to those constraints given by the g sub k's amounts to solving this system. So it's the gradient of f minus Lagrange multiplier times the gradient. Now I'm just like stepping over my words. Lagrange multiplier times the gradient of each one of the g sub k's, and you've got m of them, so you're going to subtract the sum of all of them, and should be equal to 0. So this is basically giving us a system that we have to solve. But here's where, again, things just get so cute. Using the notation that we've written here, we can rewrite this as this. And this is the dot product. So I don't know if you can see it. But this is lambda sub k times this plus lambda sub k times this plus lambda sub k times this plus dot 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 until you have m of them, right? That's a dot product. That's saying the lambda vector dotted with this gradient of all those g's vector. We're going to do gradient of f minus this dot product and set it equal to 0. Solving that gives us the maximum and minimum values if they exist. Right. So just like before, this is typically formulated in terms of the Lagrangian. And again, this is what the Lagrangian looks like. It's our function minus lambda dot g. There it is. That's the Lagrangian. It's like still the same structure, right? Then the problem of finding these maximum and minimum values really boils down to finding the roots of the gradient of the Lagrangian. So in other words, this is what you were trying to solve. That is what you were trying to solve. Yep, that's it. This with this condition right here. And what does this amount to? This amounts to solving n plus m equations in n plus m variables, which again is a problem just ripe for computers to solve, right? You know what I mean? Ripe for computers to solve. We don't want to do this by hand, but it is nice to know the formulation of the problem. All right, on that note, let's play. So that's it for Lagrange multipliers. Again, please do use the Lagrangian, formulate the Lagrangian itself, take the gradient of the Lagrangian, set it equal to 0, and it will make things very clean and clear. If you want to get deep into it, you can try to program it in your own favorite programming language, but you don't have to. Just know that you could, all right? Okay, thanks again for listening. This concludes chapter 14. So the next time I see you, we'll be talking about chapter 15, which is kind of like stepping into calculus 2 in higher dimensions. So we kind of like got kind of through calc 1 in calc 3. Now we got to go to calc 2 in calc 3, if that makes sense. Anyway, okay, enough of that. Thank you all for listening. I'll see you next time.